Good morning, everyone. Thank you so much for joining this workshop, and I hope you were all enjoying the sessions yesterday. So I'm the first speaker today. My name is Jian Wang, and I'm an assistant professor in the Department of Pharmacology. So today I'm going to talk about the transformers and attention. So I think everyone can still open this link just like yesterday, and then open up the file, the notebook named attention and the transformer. Just a stop click. Okay, so in this session, we're going to learn how to build a transformer from scratch. So why do we care about transformer? Why do we care about attention? So I don't know how many of you have heard of ChatGPT or have tried ChatGPT. So I think maybe everyone has heard of it. So there are so many media that are maybe exaggerating the ability of ChatGPT. But without a doubt, ChatGPT is revolutionizing the world. And so ChatGPT and all the other large-scale models, such as DALL-E and Llama, which is proposed by Meta, and BARD proposed by Google, So they are all based on transformers. And so transformer is a new model proposed in this paper published in 2017. So the core idea in transformer is attention. So that's why today we are going to talk about attention and a transformer. So what is attention? So here is an example. So let us look at this sentence. The animal didn't cross the street because it was too tired. So when we are reading this sentence, so for example, if we are reading this word it, so it refers to the animal. So when we are reading the it, we are paying attention to the animal. So this is the so-called attention. And the reason that we need to implement attention in neural networks is that we are trying to find the long-range connections in a sentence. So sometimes maybe there is an article with thousands of words, and when you are reading one word, it may be linked to another word that has a distance of maybe 1,000 words with this word. So and transformer can capture these connections, can capture these links. And so there are so many other types of neural networks, such as convolution neural network, such as RNN, such as LSTM. But they can also capture such types of connections, but not so long. So here we are going to learn how to build a transformer and how to build a transformer that can capture the attention inside the sentence. So before we are learning attention, so the first step is to embed a sequence. So here we are going to processing the sentence. So maybe we're going to processing this sentence. Thinking machines are revolutionizing the way we live. This sentence is shorter, so it's a better example. And so when we are dealing this sentence, so the first step is to represent each word in this sentence as a vector. So this is the way how computers are processing the sentence. So for example, we have thinking machines are revolutionizing the way we live. And each word, such as thinking, we are going to embed this word to a space, to a vector space, and then we can represent this word as a vector. And we will represent the machines as another vector. So this way we can represent this sentence as a matrix. And in this matrix, each row represents a specific word. So this is the first piece of code in this notebook. So we need to run this, and we can see the results. So to embed the sequence to vectors, and it's very straightforward. We just need to here. So it's this one-line code. we just need to use this function. So here I define this function, and it's just some functionalities that has already been provided by PyTorch. So we don't need to dive into the details. We just need to use it. Here I also define two other functions, vector to string, matrix to string. So this, the purpose of these two functions are to print a matrix. So we don't need to pay too much attention to this code, but we need to just know that in this code, we are going to embed the sentence into words, into vectors. So after we define such sentence with vectors, the next step is to defining the attention. So as I mentioned before, so when we are reading a specific word in this sentence, we are actually paying attention maybe to another word. So that means, for example, when we are reading the leaf, this word leaf, we don't know which word we should pay attention to. So maybe we need to pay attention to thinking or machines or R. So how do we decide which word to pay attention to? So the way is to, so in transformer is to use dot product. So each word is represented as a vector. So this way, if we want to know which word we should pay attention to for leaf, then we can calculate the dot product of the word leaf with each of the other words. So, so I will explain why this works. So there are many advantages by defining attention as dot product in this way. So here, this is a definition of dot product if any one of you doesn't know it. So we have a vector A and a vector B. So the dot product is the sum of the multiplication of each element in these two vectors. So here you can run this code. And after running this code, you can see that there are 4 figures. So in each of these figures, we have 2 vectors, a red vector and a blue vector. So we can see that in each of these figures, the angles between these two vectors are different. In this figure, the angle is 5. So actually, I want to define it as 0, but to represent the red and the blue, I use a very small angle of 5. So in this figure, it's 45, 90, and 180. So we can see that if we calculate the dot product of these two vectors, and if the angle is maybe 0, the dot product will be 1. If the angle is 45, the dot product is 0.7. And so we can see that when the angle is 0, the dot product is maximum is 1. So which means that we can represent each of the words in the sentence as a vector. And the two, so when we want to know which word we should pay attention to, we can just calculate the dot product for the 2 words. And if the dot product of the 2 words is 1, and then we can see that these 2 words has the same direction in the specific vector space. And this way, if these 2 vectors has the same direction, then we need to link them. We need to, when we read one of the words, we need to pay attention to the other word. So this is an explanation of the attention inside the vector space. And so as I mentioned that if we directly, so here we can see that we represent each of the words as a vector. So if we directly calculate the dot product, so maybe live and thinking. And so here maybe live should, when we read live, maybe we should pay attention to way. So in theory, when we calculate the dot product of live and way, the dot product should be maximum. It should be larger than the dot product between live and way, live and live and are, live and revolutionizing. However, since when we embed the words into a vector space, this is not necessarily the truth. So the dot product of live and we may not be larger than the others. So we need to let the machine learn it. We need to define some parameters so that when we calculate the product of live and we, then we can get the maximum dot product. So the way we are going to manipulating the vectors in the vector space is to do linear transformation. So a linear transformation is a matrix transformation. So when we perform linear transformation, we just, so if we have a vector, when we perform linear transformation, we just multiply this matrix, which represents the transformation by the vector. So it's just, the linear transformation is just the product of the matrix and the vector. So the advantage is that by using linear transformation, we are actually rotating, or we are actually scaling, or we are actually trying to get the reflection of the vector. So if you run this code, and then we can get these three plots. And in the first plot, we can see that we have two vectors, the blue one and the red one. So initially, they are not aligned, so the angle is not 0. And so if we want to get a 0 angle, so we can do linear transformation for the blue and the red vectors. So here, for example, we have defined two linear transformation matrix, and here I print them. So these are the two linear transformation matrices. And we can see that after the linear transformation, the red vector has the same direction, but it just has a different magnitude. So here is 1 and here is 2, but the direction hasn't changed. And after the linear transformation for the blue vector, we can see that the direction has changed. And now the blue vector and the red vector has a zero angle, so they are aligned together. And if we calculate the dot product, it will be maximum compared to other dot products in the sentence. So the key in the transformer is to get a linear transformation that we can convert each of the words in our sentence to a specific vector, so that it can get the maximum dot product for the two words that we want to pay attention to. So here, if you read some articles about transformer, you may encounter some terminology such as query, key, and the value. So, and the query, key, and the value are actually what I just explained. So, for example, here are two words, thinking and machines. So the initial step is to embed thinking machines to vectors. So as I mentioned before, we need to do linear transformation. So for example, for thinking, for this word, this vector x1, so we can do a linear transformation so that we can get another vector q1 for x1. Similarly, we can get q2 for x2. So this is the transformation 1. So remember that for these two vectors, we need to do different linear transformation for the two vectors. So here, for query, this is transformation 1, and we need to do another transformation 2. We can get the keys for the two vectors. So for x1, we can get k1, x2, we can get k2. And so here, there is a matrix wq and wk. And actually, they are the parameters, they are the values in these transformation matrices. So by multiplying the wq and x1, we can get q1. By multiplying wq and x2, we can get q2. So this we have different vectors by doing different linear transformations. And so usually in the papers of transformers, these vectors are called queries. These vectors are called keys. So what we are going to do next is to, based on the queries and the keys, we can calculate the attention. So for example, when we are reading the word machines, we want to know whether we should pay attention to thinking, then what we can do is that we can calculate the dot product of Q2 and the K1. So this way we can get a score. And if we are reading thinking and we want to know whether we should pay attention to machines, then we can calculate the dot product of Q1 and K2. So this way we can get a score for each pair of the words in the sentence. So finally we will get a matrix. So if you run this code, we can see that so initially each word in the sentence is embedded to a specific vector, and then we can calculate the query vector, the key vector, and the value vector for each of the words in the sentence. So I haven't mentioned value, and I will mention value later. And so just as I mentioned, we can get a score for each pair of the words in the sentence, and this score will represent whether we should pay attention to to one word if we read another word. So here, if you run this code, we can see that there will be this matrix. So in this matrix, each row represents a specific word. Each column also represents a specific word in the sentence. We can see that we can get this matrix, which is called the attention matrix, by just multiplying, by just calculating the dot product of each pair of words in the sentence. So, so based on these values, for example, here we can see that for this entry in this matrix, it has a very high attention scores. And so it means that when we are reading machines, we need to pay attention to thinking. This may not be true, and it's fine, because our purpose is to let the machine learn the process, learn the parameters, and then it can generate the correct attention matrix. So this would be an initial attention matrix. And we have, so I think Mike will, in the maybe afternoon, right? Mike will talk about the neural networks and maybe talk about how to train the neural network. So after we train the neural networks, we can get the correct attention matrix. So in this attention matrix, there are many minus scores, positive scores, and some scores are larger than 1. So actually, so we need to do another, we need to normalize this matrix, and we can use the softmax function in PyTorch score so that we can get a normalized attention matrix. So in this normalized attention matrix, if the score is 1, it means that it has a maximum attention. We need to pay attention to one word if we read another word. So after we get this attention matrix, what can we do with this attention matrix? So remember that attention means that if we read one word in a sentence, we need to pay attention to another word. So, so that's why we need to define the value vectors. So it means that when we are reading thinking, for example, if we need to pay attention to machines when we are reading thinking, we need to connect the information from the machines to thinkings. So maybe there are other words, and we need to connect information from each of the words in each of the other words in the sentence to thinking, and the value. So how much information should we connect from the other words in thinking? So that value is defined by the attention. So which means that here we have after the normalized attention matrix, we can get a score. So the picture here is wrong. So actually, this should be a value between 1 and 0. And so, for example, if, when we are reading thinking, if the score from machines is 0.9, if the score from another word, maybe R, are 0.1, then it means that we need to connect 0.9 information from machines and 0.1 information from R. Then we can connect all the information and multiply them by the attention scores to thinking. So when we are multiplying the information, we are multiplying the values by the attention scores. Then we can get a new vector for thinking, so which we will name Z. So if we run this code, okay, oh, it should be here. Yeah, the score point 88.12. So we will get a new vector z. So z represents the vectors for each word that we have already connected the information from all the other words in the sentence. So here, if you run this code, we can see that for each word thinking, this is the initial vector that we have embedded it in the vector space. And we can finally get a z vector for thinking. We can get a z vector for machines. And so this way, we have done a process named attention. So this is just the most basic blocks in a transformer. And this is actually the cornerstone of every other things in the transformer. So actually, here we can see that all the calculations are done by vectors. So actually, when we are running a real model, a real transformer model, all the calculations are done by matrix. So remember that we have a sentence, and so here, each word in the sentence is represented by a vector, and actually we can have many vectors. So we can stack all the vectors together so that we can get a matrix. And if we directly multiply the vectors by the linear transformation matrix, then we can get another matrix. So if we multiply different linear transformations, we can get query matrix, key matrix, value matrix. So all these calculations are done by matrix. So each is much more efficient when we are dealing with matrix because we want to use GPU. So if you run this code, here this is all the process. So initially, we have the embeddings for each word in the sentence. So each word is represented by a vector. And then we can get a query matrix. So note that all the all the vectors have been stacked together. So here we are dealing with matrices. And we can get a keys matrix, values matrix. We can finally multiply the keys and the queries to get the attention scores. So, and then if we multiply the attention scores by the values, we can get the z matrix. So overall, all the process that I have mentioned can be concluded in this formula. So we just first multiply Q, query, and the key, and then we get the attention scores, we normalize it, and then we multiply the attention scores by the values, then we can get the z's. Okay, so these are just the basic knowledge of attention. So I think maybe by here, so this is all I want to talk about today. So actually this may be an end, but I want to talk a little bit more about the implementation of the attention in PyTorch. So actually in PyTorch, not only do we process all the attention stuff by matrix, but also we are processing them by batches. So yeah, I think Mike will also talk about batches today. So we can see that all those calculations are done in this function, so which is named scale.product attention. So if we have query, key, and the value, and then we can use this function to calculate the attention. So there are only 4 lines. So this is the core of the attention in PyTorch. And so if we run this code and run this code, so this is the test of this function. So we can see that if we have 2 sentences, thinking machines are revolutionizing the way we live. The transformer is a powerful deep learning model. And for each of the sentences, we can represent, first embed them to a vector space. And so we can represent this sentence by a matrix. We can represent the other sentence by another matrix. So we stack them together, then we can get a matrix with a shape of 2 by 8 by 4. 2 means that we have 2 sentences in this large matrix. And 8 means that for each sentence, we have 8 words. 4 means that for each word we embed it to a vector space, a 4-dimensional space. So actually 4 could be 8 could be 16. So we can embed each of the words into a vector space with a different dimensions. And I remember that in ChatGPT, each word is embedded in a vector space with a dimension of 1024. So that's why the training of ChatGPT needs thousands of GPUs. So we have the embeddings, which is a matrix of 2 by 8 by 4. And then we can use this function to calculate the attentions, which is also another matrix of 2 by 8 by 4. So this is how PyTorch is calculating the attentions. So everything is inside a tensor, and everything is, all the calculations are done by GPU. And so actually that function is wrapped in a class named attention head. So what is attention head? So if we mention attention head, we need to mention multi-head attention. So remember that for each word in the sentence X, we need to calculate the query, the key, and the value. So multi-head attention means that we calculate multiple queries for the words in the sentence. So here we have Q0, Q1, maybe we can have Q2, Q3, Q4. And we have K0, K1, K2, K3. So this way we can, this is named the multi-head attention because we have different attentions for this embedded vectors. So it means that we can consider different aspects for the attentions in the sentence. So for example, for the 2 sentences here, maybe thinking machines are revolutionizing the way we live. So when ChatGPT are generating the word in the sentence, for example, so ChatGPT is generating the sentence 1 word by 1 word. So it will first generate thinking, and then machines, and then R, and then revolutionizing. So when they are generating revolutionizing, so they need to pay a little bit attention to R, so that it will know that it will add ing to this word. So this is one aspect regarding the grammar. And however, so in the other aspects, so when ChatGPT is generating the revolutionizing, it maybe also need to pay attention to thinking machines. So because it's thinking machines that are revolutionizing the way. So this way, it corresponds to multi-head attention, because by using different attention, we can pay attention, we can consider a different aspect of what we need to pay attention to. So this is why we need multi-head attention. And so after the multi-head attention, we can get many different Z vectors. So we just need to stack them together. So here we are going to run this code. So this is a definition of multi-head attention. And if we run this code, here we can see that, remember that the embedding matrix is a matrix with a shape 2 by 8 by 4. So after attention 1, we can have the matrix 2 by 8 by 4. After attention 2, we can get another matrix 2 by 8 by 4. So we just concatenate these 2 matrices, then we can get a matrix of 2 by 8 by 8. So we will do some linear conformation so that we can still get a matrix of 2 by 8 by 4. And then, so this will be the final Z vectors that we will get after a multi-head attention. So now we are going to look at the architecture of a real transformer. So this is a figure from the transformer from the paper published in 2017. The attention is all you need. So we can see that. Let me zoom out. So this is the architecture of a transformer. So what we need to pay attention to is NX. So NX means that we have N such blocks. So actually a transformer is just a stacking of these types of blocks. So what is this block? So each of these blocks is a multi-head attention. So which means that transformer is just a stacking of many multi-head attention layers. So, and apart from the multi-head attention, we can see that there are some add and norm, there are some feed forward, there are positional encoding. So we will dive into these terminologies. So first is positional encoding. So why do we need positional encoding? So we can see that the positional encoding is in front of all the other layers in this transformer architecture. So what is positional encoding? Remember that we can get the attention scores for each of the pairs of words in the sentence. So each attention score is calculated by multiplying, by calculating the dot product of the two vectors that represent the word. However, imagine that if we maybe switch the order of machines and R, and then the matrix will be the same, except these two rows and these two columns will be switched, but the values will be the same. And actually, this is not what we want, because if we are generating the sentence thinking machines are revolutionizing the way we live, if we switch the order of machines and R, actually it's a wrong sentence. And if we just use this method, the transformer cannot detect this error. So we need to consider the information of the position of each word in the sentence. So machines should be in front of R. And so how do we consider this position information? So there are two ways. The first way is that we just need to, when we encode each vector, each word in the vector space, we can add some additional features. So for example, when we are, so this is a vector for the first word. So when we are embedding this word in the vector space, we can add some additional features. For example, this is the first word in the sentence, then we can add an additional feature. And so it means that we add a value 1, we add a value 2 for the second word, we add value 3 for the third word. And so this is one way that we can include position information into the calculation. So, however, in transformers, they are actually using another method named positional encoding. So it's very hard to talk about which method is better. So here I'm going to explain how they use positional encoding to include the position information into the matrix. So in the first word, if we add additional features to the vectors that we have embedded, it has actually changed the dimension of the vector space. So for example, if we embed each word into a vector space of dimension of 4, and if we add additional features, it's actually another vector space with a dimension of 5. So by using positional encoding, we are not changing the dimension of the vector space. So we are actually just generating another matrix and add this matrix to the matrix that we have embedded for all the words in the sentence. So here in this matrix, so the first row represents the information, the position information that we need to add to the first word. The second row represents the position information that we need to add to the second word. So each row is different. So by using this way, we can consider the position information in the embeddings. And so this is positional encoding. And next is feed forward. Feed forward is very straightforward. It's just a stacking of some linear transformations. And so there's nothing special. And the third, there's another terminology named the residue. And the residue is a basic blocks in nearly all types of neural networks. So based on residue, can we develop the technique named deep learning. So without residue, we cannot stack so many layers into a neural network. So because the gradients will vanish if we stack too many layers in a neural network. So here is a paper of residue. So we can see that there are, so it's published in 2016, and the citations already been 160,000. So, and the residue is nothing special, it's so straightforward. So it's just, so here could be any neural network. So we have the input X, we have any type of neural network, and then we can get the output of X, which is fx. So any neural network is just a function mathematically. So residue means that after we get fx from X, we will add fx to X as the output. So this is named a residue network. So the advantage of residue network is that we can avoid the gradient vanishing problems, and so that we can stack maybe hundreds of layers to a neural network. And so this is the implementation of residue networks. So because the idea is so simple, and so also the implementation is also very simple, just one line of the code. And so this is a test of the residue network. And we have X, and then we have Y, and actually there are vectors with the same dimension. And another terminology is encoder. So encoder is just the stack of different encoder layers. And inside the encoder layer is a multi-head attention layer and a feed-forward attention layer. So we have already talked about multi-head attention, and we have talked about feed-forward neural networks. So encoder layer is just a combination of these two neural networks. And of these two layers, all these two layers are implemented by residue connection. And so encoder is just a stack of many encoder layers. And so this is the implementation of transformer encoder layer. And this is the implementation of transformer encoder. So in the encoder, we can see that there is a layers, and the layers is composed of many encoder layers. So yesterday, Mike has talked about the basic workflow in the class, in the neural network class in PyTorch. So we need to define the constructor, and we also need to define everything in the forward. And so here, this is a test of the encoder. So this is the embedding of our sentence, which is a matrix of 2 by 8 by 4. This is a sentence. This is a new vector, new matrices after we have subject the matrix to the encoder. And similarly, we can define decoder. And actually, there is nothing special about decoder. It's very similar to the encoder. And actually, in many new transformers, decoder has been deprecated. So they only use encoder. So we can just use encoder in transformers because both encoder and the decoder are using multi-head attention. So it's fine if we don't use decoder. We can just use encoder. So here is a testing of the decoder. So there is no errors. It means that there are no errors inside these codes. And you know what? All these codes, decoder and encoder, I didn't write a single word for all these codes. I just asked ChatGPT to generate all these codes. So this is the way how programmers right now are programming. So when we are trying to write a function, we don't need to write one word by one word. We just need to tell ChatGPT what we want to do. So it will generate the code for us. And what we need to do is that we can review all the code and do some necessary modifications to the code. And here, this is wrapping up of all the stuff that I have talked about before. So this is transformer. A transformer is composed of an encoder and a decoder, and an encoder is composed of many encoder layers. And inside an encoder layer, we have multi-head attention and we have feed-forward. So all these codes, as I mentioned, all these codes are generated by ChatGPT. And then, so these are the codes as I wrote. So let's test. We can see that there are no errors. It means that the transformers are working. So it means that we can directly use all those words inside our projects. And then what we need to do is that we need to prepare a data set, and we need to write some training codes for this transformer. So, and that will be the sessions that will be introduced by Mike. So about the training of the neural network. And so in the next step, I will talk a little bit about one application of attention in biology. So this is the paper that we published last year. So in this paper, we use attentions to predict the binding affinity between a protein and a compound. So here is a workflow, and it's also very straightforward. We have the protein sequence, and we have the compound, and then we can embed the protein sequence to a vector space. We can embed the compound to a vector space, and then we can multiply them to get the attention matrix. And by using this attention matrix, we can predict the affinity. So in this attention matrix, each entry represents the attention score between a specific protein residue and a specific compound atom. So below are implementations of the model in this paper. So actually, when we published this paper, we are using another framework named Sonnet. We didn't use PyTorch. So when I developed this model, I spent several months, and so write a lot of codes. However, here I'm showing you the PyTorch codes, and these codes are generated by ChatGPT by less than 1 minute. So instead of writing all the codes by month. So here we can see that these are the first step. We can encode a protein. So how do I get these codes? I just ask, can you write a function for me to encode the protein sequence to vectors? Then it will give me all these codes. So we can see that this is a protein sequence, and it embedded. It uses one hot method to embed this protein sequence to a vector space. Then we can get this matrix, which has many zeros because we use one hot. One hot means that, for example, for the first row of this matrix, we have this one in this position. So in this row, we have 20 entries, which each entry means a specific amino acid type. So one in this position means that this amino acid is of this type, and this amino acid is of this type. So this way we can get a matrix with a shape 16 by 20 for this sequence. And similarly, we can embed the compounds. But to embed the compound, we need to use some different packages named RDKit. So RDKit is a Python package that is used to deal with small molecules. And here we are trying to embed a compound. So for this compound, we need to provide the smiles. So this is dopamine. And if we use RDKit to draw the structure of this compound, it looks like this. And here, these are the codes that how we can embed the compound to the vector space. So compound is different because for protein, it's just a sequence. And however, for compound, it's a graph. So we can represent as a graph is not one-dimensional. A compound will have many atoms, we have many edges. So to deal with such structure, we need to use a technique named the graph neural network. So by using a graph neural network, we can generate, we can embed the compound to a vector space. So here I'm not going to dive into the graph neural network because our focus is the attention and the transformer. And you can read some literature of graph neural network. So by using a graph neural network, so here these are the atoms in the compound. We can embed each of the atoms into a vector space. And this is after the embedding of this compound by using the graph neural network. So we can see that initially for each atom, we just assign different values as features to the vector space. So for example, 6 means that the mass of this atom is 6, so it's a carbon. So this is carbon, and this oxygen. And so the graph neural network will transform these vectors to a different vector space. And then we can get a protein matrix, and we can get a compound matrix. The protein matrix is of the shape 16 by 32. The compound matrix is of the shape of 11 by 32. So which means that we have 16 residues in the protein, and we embed each of the residues in this protein sequence to a vector space with dimension of 32. And we have 11 atoms in the compound, and we embed this compound to a vector space of 32. And then next step, we can get the attention. So we just need to multiply these two matrices. But before the multiplication, we need to do transpose for the compound. So that is 16 by 32 times 32 by 11. Then we get a matrix of 16 by 11. So this 16 by 11 matrix represents the attention matrix. So in this attention matrix, each entry represents the associations between a specific protein residue and a specific compound atom. So that's all we need. So next step is that we just need to prepare the data set for about protein and compounds, and we need to write some training code to train the neural network so that it can generate the correct attention matrix, and then we can predict the binding affinity by this attention matrix. Okay, so that's all about attention and the transformers that we're talking about today.